In this video, we'll be talking about integrating our different system elements together. We've got software, we've got hardware, we may have things from different vendors. How do we actually join it all together and get it all work together? Well, one of the things that we've talked about previously is having our interface design document and using these documents to look at how all the things will actually interface together. What protocols they'll use, what wires they'll use if it's a physical hardware system, or what nuts and bolts they'll use. All of these things are important to make sure that our different modules and our different subsystems actually connect to each other and actually join together. Now, there's many different examples we could choose, but one that includes both software and hardware in a very meaningful way is integrating or building some sort of a robot system together to form some particular purpose or function. And so clearly we'll require hardware to achieve this because robots have a hardware component to them. It's mechanics that's actually moving. But that mechanics that actually moves needs to be controlled somewhere. So the hardware won't do anything unless we have software that's actually controlling it. And with the wrong software, well, we can have very dire consequences. And unfortunately, we see people being killed by robots or seriously injured by robots, particularly these larger scale industrial robots. This is something that at all costs we want to be able to avoid. And so here is a circumstance where we don't just want to turn it on and see if the software works. We actually want to model it and test it before we actually turn it on and put people potentially in harm's way. And so we'll need to make sure those software and hardware design teams communicate effectively and actually communicate their needs and requirements and their interfaces to each other so they know how each other is working. One of our students was recently working on a project in Germany at the Fraunhofer, and they were talking about one of the issues between the hardware and the software that they were using, the software they were designing, was endianness. This is a concept I cover in digital electronics and controllers, but it's the byte or bit order that we're actually storing or transmitting our data in. And they need to write a function to convert it over. And this is something that they realized after a little while that the data seemed garbled when it was coming out, and once they converted it over and reversed the endianness from big endian to little endian, it worked perfectly fine. And so we really require our hardware team first up to understand the physical requirements of the robot, but we also need our software team to understand the software elements to this and how we're actually going to control the hardware and what the hardware is actually going to do. Our hardware team will need to know, for example, the amount of force that is required to perform a particular operation. If they're designing a gripper or something, how much force do they need to put on something and how is it actually going to grip? Our software team needs to know the interface of this hardware to actually control it and make it work. And any changes to these interfaces will need to be communicated back and forth so both teams actually understand what changes have been made and what changes will actually affect them. Another important aspect that is useful here is prototyping. So throughout our detailed design process, it's actually very useful to create a series of prototypes. And they basically allow us to trial parts of the system and confirm that that part of the system, or at least that part of the system, is bug-free and ready to achieve the particular mission that we've set for it. It'll satisfy the needs and requirements of that subsystem. It also gives us a proof of concept and confidence in that proof of concept design that this thing actually is possible and will work, that we won't have huge surprises when we get to the construction phase and work out, hang on, these things that we hoped that we could do are actually impossible and we can't do. And it also allows us to debug at a more localized level. It reduces the size of our search space and helps us find bugs a whole lot easier and be confident in those small scale prototypes that things are actually going to work. And things will work as we integrate them into the larger system. So, for example, our new GPS system, our satellite navigation system, it'll build confidence if we can show some software that's properly integrated with a piece of hardware. Even if the software has limited functionality, if we can show the basic functionality there, it will build some confidence that, yes, there's integration happening properly between the software and the hardware, and we can, for example, read our GPS measurements and display some basic maps. Other things can come at a later stage, but these are important prototypes towards integrating our two systems together. And over time, that integration will be shown through all the different functionality, all the advanced mapping and on-the-fly navigation and on-the-fly real-time mapping of traffic conditions and things like that as well. For example, another place that we might see this prototype happening is in a SpaceX program. So 2017, if all things go to plan, they're planning on launching a prototype satellite. And the idea of this prototype satellite is to give them data and actually demonstrate that they have the capability to do this. It'll also allow them to demonstrate whether the technology will work in the sort of conditions that it needs to work in. And hopefully it will lead to the launching of a whole series of satellites providing worldwide internet access. Now, it would be a bit foolhardy to launch all those satellites all at once without actually launching a prototype first, because they may discover some bugs with that prototype, which will cause them to have to recall all those satellites or relaunch a whole series of new satellites. It's a whole lot safer to actually launch one or a small series of these satellites, evaluate them in the field for a while, and based on the performance of their prototype, make any changes that need to occur, and then launch their full system at a later date. And this is essentially verification validation in action. Or whatever form our prototype is actually taking, we want to perform our validation on it and a verification, making sure that our system meets the requirements, but it also meets the validation criteria, saying, yes, we're actually fulfilling that particular requirement. We're fulfilling what the customer wanted, and we're fulfilling it to the correct standard that the customer wanted us to evaluate it according to. So we've built the right thing, and we've built the right thing correctly.